After studying this module, you will learn the derivation of the Michaelis-Menten equation, which is used essentially in understanding enzyme kinetics and its applications. The significance of the factors V0, Km and Vmax to determine the catalytic efficiency of enzymes. Let me introduce you to this module. In 1902, Adrian Brown had reported an investigation on the hydrolysis of sucrose by the plant enzyme invertase to products glucose and fructose. Sucrose, glucose and fructose are optically active, but since fructose is more levorotatory than either sucrose or glucose, which are dextrorotatory, the hydrolysis of sucrose can be followed by the change in optical activity from dextro to levorotation. Hence, the enzyme catalyzing this equation or reaction is known as invertase. Brown found that when the concentration of sucrose is very high, the rate of enzyme reaction is independent of substrate concentration. However, at low substrate concentration, enzyme activity is directly proportional to substrate concentration. This observation was extended by Leonard Michaelis and Maud Menten to derive the famous Michaelis-Menten equation. In deriving the equation, several assumptions were made which will be highlighted. Let us look at the derivation of Michaelis-Menten equation. The first is the relationship of velocity with substrate concentration. Based on Adrian Brown's work on the velocity of an enzyme catalyzed reaction of sucrose to glucose and fructose, Michaelis and Menten in their pioneering work determined that the progress curve between velocity v and substrate concentration S was a rectangular hyperbolic curve as depicted in sucrose is acted upon by the enzyme invertase to give glucose and fructose. If you observe, relates the velocity on the y-axis to the molar concentration on the x-axis, you can easily see a rectangular hyperbolic curve wherein at initial substrate concentrations or lower substrate concentrations, the velocity is linearly increasing. As the substrate concentration increases, you find that the line becomes parallel to the x-axis. At this point, when the curve becomes more or less horizontal to the x-axis and thereby reaches a maximum velocity Vmax, this behavior was interpreted as the overall reaction is composed of two reactions. 1. The enzyme binds the substrate forming an enzyme substrate complex. 2. The complex breaks down to form the product and enzyme. As per the figure, when the enzyme is fully saturated at high substrate concentrations, the overall reaction is insensitive to further increase in substrate concentration. At this stage, when the velocity is Vmax, all enzyme is in the ES or enzyme substrate complex. The general velocity or rate of a reaction V is equal to V equals K into change in product concentrations by dt, wherein V is the velocity, dP by dt is the change in product formation with time, K is the rate constant. In an enzyme catalyzed reaction, there are several rate constants and these are designated as in the overall enzyme reaction of a single substrate catalyzed enzyme reaction. First of all, enzyme plus S gives rise to ES, which can then break down to give you E and product. E plus S giving rise to ES, the forward reaction has a rate constant K1. ES dissociating to give back E and S has a rate constant designated as K1 is the rate constant for the formation of ES, K minus 1 is the rate constant for the dissociation of ES complex, K2 is the rate constant for the formation of product. Now let me introduce you to the steady state hypothesis. Consider the graph which relates concentration of various species in the enzyme reaction to time. The progress of various participants ES, E, P and S with time under physiological conditions wherein S is saturating or much higher in concentration than E. At an initial stage lasting about a few milliseconds, the mixing of enzyme and substrate, the concentration of ES rapidly rises and stays more or less constant over a fair amount of time. This was described by George E. Briggs and John B. S. Haldane as the steady state, and therefore change in concentration of ES by dt is equal to 0. This was an assumption made with a fair degree of accuracy and is called the steady state hypothesis. During a period wherein substrate is in excess of enzyme, this is true. Only when the substrate depletes and excess product is formed will the assumption be invalid. Let us now derive the rate equation. At any point in the enzyme catalyzed reaction, equation holds. E total is equal to E plus ES. E being free enzyme, ES enzyme substrate complex and ET the total enzyme present. For any equation to be experimentally useful, quantities that are not directly measurable are avoided and therefore the exercise is undertaken to replace E, ES and ET step by step. First of all, dES by dt is equal to 0, an assumption of the steady state hypothesis. All reaction rate leading to the formation of ES are balanced by reaction rates removing ES. Reaction leading to ES formation, K1 into E into S. Reactions removing ES, K minus 1 ES and K2 ES. Therefore, K1 E into S is equal to K minus 1 ES plus K2 ES, or rearranging K1 E into S is equal to ES into brackets K minus 1 plus K2. Replacing E with Et minus Es, K1 brackets Et minus Es brackets close into S is equal to Es brackets K minus 1 plus K2. Rearranging and substituting for K minus 1 plus K2 divided by K1 as Km, or the Michaelis-Menten constant named in the honor of the scientist who worked these equations. Km Es is equal to brackets Et minus Es brackets close into S, or brackets Km plus S brackets close into Es is equal to Et into S, or Es is equal to Et into S divided by Km plus S. The initial velocity V0 is equal to K2 Es, and maximum velocity Vmax is equal to K2 Et, as all enzyme is bound by substrate, and therefore Es is equal to Et. Substituting for Es and Et, V0 is equal to Vmax into S divided by Km plus S, which is the Michaelis-Menten equation. This equation is the basic equation of enzyme kinetics. Let us look at the significance of Km. Under conditions where K2 is low or in the initial part of the reaction, Km becomes approximately equal to Km equals K minus 1 divided by K1, or the dissociation constant of the Es complex. Or in other words, if Km is I, the affinity of the enzyme is low, and vice versa. Hence, the same enzyme from different sources can be compared on their substrate binding affinities, as is observed in the table. Let us look at the substrate, namely radioactive phenylalanine assay, and the enzyme from sources such as wheat germ, soya bean and yeast. The enzyme assayed is the enzyme phenylalanine transfer RNA synthetase. If you look at the source wheat germ, the enzyme has a Km of 5.2 micromolar. From soya bean, it has a Km of 0.9 micromolar, and from yeast, it has a Km of 5.5 micromolar. Therefore, the enzyme from soya bean having the least Km shows therefore the highest affinity. Also, at half maximal velocity, that is when V0 is equal to Vmax divided by 2, and substituting this in the Michaelis-Menten equation, Vmax divided by 2 is equal to Vmax S divided by Km plus S, or Km is equal to S. Thus, if Vmax can be determined, the substrate concentration at half maximal velocity can be determined, and thereby the Km. How do we determine Km and Vmax? An inspection of the figure indicates that Vmax cannot be easily determined from the graph, as the exact point wherein the curve turns parallel to the x-axis is difficult to determine. Hence, a linear plot would be easier to analyze. Hence, Lineweaver and Dean Burke used the Michaelis-Menten equation and converted it into a double reciprocal format. V0 is equal to Vmax into S divided by Km plus S. This is the basic Michaelis-Menten equation. Now, taking reciprocals on both sides, 1 over V0 is equal to 1 over Vmax S plus 1 divided by S. This is known as the Lineweaver-Burke or double reciprocal plot as illustrated. A typical plot of 1 over V divided by 1 over S for an enzyme gives a linear plot which can be extrapolated to the x-axis. The line where it meets the x-axis is equal to minus 1 over Km. The linear line where it meets the y-axis is 1 over Vmax. Hence, Vmax and Km can easily be determined using this double reciprocal plot. Now let us look at the catalytic efficiency of enzymes using these parameters of Km and Vmax. Enzymes catalyzing similar reactions from different sources have different Kms, suggesting that some enzymes have higher affinities for substrates. However, the Km cannot be an index of catalytic efficiency as it does not directly relate it to K2 or the rate constant for an enzyme catalyzed reaction. The catalytic rate constant is Vmax equal to K2 into Et. When Es is equal to Et at high substrate concentration, K2 becomes Kcat or the catalytic rate constant. A survey of the table suggests that low Km, which indicates high substrate binding affinity, does not necessarily translate into high Kcat. Let us look at the table. The enzyme is carbonic anhydrase, the substrate is carbon dioxide, the Km is 1.2 into 10 to the power minus 2 molar. Kcat, which is having a unit of per second, is 1.0 into 10 to the power 6. Catalase, whose substrate is H2O2, has a Km of 2.5 into 10 to the power minus 2 molar and a Kcat of 1 into 10 to the power 7 per second. Another enzyme, fumarase, which has the substrate fumarate, has a Km of 5.0 into 10 to the power minus 6 molar and a Kcat of 8 into 10 to the power 2 per second. Urease, whose substrate is urea, has a Km of 2.5 into 10 to the power minus 2 molar and a Kcat of 1 into 10 to the power 4 per second. You can easily observe that where the Kcat is high, for example, in the case of carbonic anhydrase, the Km is 1.2, where the Kcat is 1 into 10 to the power 7, the Km is yet similar at 2.5 into 10 to the power minus 2. This is when you compare the values for carbonic anhydrase and catalase. Again, look at urease. The Kcat is quite low, that is 1 into 10 to the power 4, per second. However, the Km is similar to that of catalase, 2.5 into 10 to the power minus 2. This table therefore indicates that Km and Kcat are not necessarily related. In view of this, what is the significance of Kcat? As has been indicated previously, Vmax is equal to Kcat into Et. Rearranging, Vmax divided by Et is equal to Kcat, or Kcat is the number of substrate molecules which are converted to product per unit time. By convention, Kcat is expressed therefore as the turnover number with units of per second. Unlike Km, the Kcat value directly relates to the rate of the reaction catalyzed by an enzyme and therefore is a better parameter to rate enzymes. However, the Kcat value does not tell us the rate of substrate conversion in the absence of enzyme. Some substrates can convert to product more easily without enzyme than others. The role of an enzyme is to speeden up reactions, not alter the spontaneity of the reaction. Hence, Kcat values, although better than Km values to assess enzymes, yet fall short. A better parameter to assess the catalytic efficiency of an enzyme is the value known as the catalytic constant, which is equal to Kcat by Km. If the value of Kcat by Km or the catalytic constant is inserted into the table given previously, it appears that among the enzymes the highest efficiency is that of catalase followed by fumarase. Now consider the equation, being the short form of the Michaelis-Menten equation. V0 is equal to Vmax S divided by Km plus S. During the early part of the reaction, wherein Km is much larger than S, the equation can be rearranged as V0 is equal to K2 divided by Km into Et into S, and that being equal to Kcat by Km into E into S. Thus, the parameter Kcat by Km becomes the second order rate constant for the substrate S to interact with the enzyme E. The units of this catalytic constant are the same as the diffusion controlled rates in solution, which have a maximum value between 10 to the power 8 to 10 to the power 9 for most substrates in solution. Hence, if enzymes have their catalytic constants in this range, they have reached catalytic perfection. Why? Every encounter of an enzyme with its substrate will result in product. It has been suggested that enzymes behave like sinks, guiding substrates to their substrate binding sites in the enzymes. Hence, every encounter between substrate and product can result in effective product formation. Let me summarize for you what you have learnt in this module. The Michaelis-Menten equation is useful to understand the kinetic behavior of enzyme reactions. Km and Vmax can be determined after plotting experimental results using the double reciprocal Line-Weaver-Burke plot. The catalytic constant Kcat by Km can be used to rate the catalytic efficiency of enzyme catalyzed reactions.